Well, good evening, everybody, and I'm delighted to welcome you all here tonight to what will be, I know, a fascinating and a fantastic lecture, because all lectures by Jim are. No pressure, Jim. I'm Leslie Eloise. I'm Vice Principal and Head of the College of Science and Engineering here at the University of Edinburgh. And it's a particular pleasure as Head of College to introduce star performers. That is a dreadful pun, I know, I'm sorry. But to the university, and particularly tonight when we have somebody who has made their reputation in physics, and it's the engineers who have invited him. And I think this shows that our interdisciplinary work is absolutely taken hold when schools invite people from other disciplines, and that's really what I think this is all about, encouraging. So, very big welcome to you here, Jim. Now, Jim, for most of you know, is from the University of Glasgow, and he has enjoyed a very distinguished career there in experimental physics. And he's probably known to all of you in the audience for his work on detecting gravitational waves. Now, Einstein, of course, was the first who predicted such waves more than a century ago, but it's taken us this long to experimentally prove their existence. But Jim knew right from the word go that they were there. And he knew that they would be observed. In fact, he was so confident that in 2004, or so the story goes, he placed a bet that they would be detected before 2010. The odds he got were 500 to 1. So he nearly made a very significant sum of money. What he did do was to generate so much interest in this story that the betting company were forced to cut their odds to 6 to 1. And as usual, the only winner was the betting company. Jim is, of course, a graduate of the University of Glasgow, where he became Professor of Experimental Physics in 1986. Currently, he's the emeritus holder of the Kelvin Chair of Natural Philosophy and Director of the Institute of Gravitational Research at Glasgow. His distinguished career has been marked with many honours and awards, such as member of the LISA International Science Team, delegate to the LIGO Council, Fellow of the Royal Society of Edinburgh, and Fellow of the Royal Society and the Royal Society of Arts. He's been awarded many prizes over the years, including the Duddell Prize of the Institute of Physics and the Gunning Victoria Prize Lectureship of the Royal Society of Edinburgh. And most recently, from the Royal Society of Edinburgh, he was awarded the Royal Medal, a great achievement indeed, and well deserved. He's served his community with passion and with dedication through membership of SAC, through the advisory committee of the Glasgow Science Centre, through the Institute of Physics Council, through the Council of the European Physical Society, and he was CEO of SUPA. He was awarded the OBE for services to science in the Queen's Birthday Honours in 2013. And the question when I was researching all this and writing it down came to my mind was, how did you ever find the time to detect the gravitational waves? So it's my very great pleasure to ask and invite Jim to give his lecture, The Engineering Challenges of Detecting Gravitational Waves. Professor Jim Hough. Please.
Thank you, Leslie. Thanks very much.
Thank you.
Now, thank you very much for inviting me here. I'm absolutely delighted to come. And just as an addendum to what Leslie was saying about the bet, actually the betting company decided they would try to pay out last year, but found it was too much money and they couldn't find the money. But they did try very hard, in fact, to pay out on it late, which was actually very good that they thought that. Anyway, what I want to talk about today is how we detected the gravitational waves and what some of the engineering challenges were. I've been doing this for about 46 years, and it was wonderful actually to find where it last got there last year. Now, what I want to do is talk a bit about the science, the sources, and the history of the detectors. Then I'll talk about the detections, then about the engineering, really, of LIGO, which made the detections. Then I want to talk about a little bit about the future, mainly on the ground, but I'll mention a little bit about what will happen in space, quite a few years ahead now. Now, I think everybody knows about Newton's theory, you know, that masses attract each other. And of course, it's the reason that, that satellites go around the Earth and the Earth goes around the Sun. But Newton himself felt there was something wrong because he knew that sound, you know, took a finite time to travel. I think he knew that light took a finite time to travel, yet his gravitation theory would suggest that gravitational things would travel instantaneously, and he was bothered by that. And in fact, it wasn't until Einstein came along with the special relativity in, I think, 1905 that this got resolved, because Einstein, of course, pointed out that information can't travel faster than the speed of light. So there must be some way that gravitational information is transmitted. There must be some sort of gravitational radiation, but Einstein at that stage didn't know what. And in fact, it took 10 years, really, till general relativity came about. You know, the 1915 theory, that by 1916, Einstein was able to predict that gravitational waves would be produced by the asymmetric acceleration of matter. But I have to say that there was widespread disbelief about their existence. Eddington felt they could be transformed away at the speed of thought, for example. And yet somehow they didn't worry. When thinking they didn't exist, they still didn't worry about how information was actually transmitted. Interestingly enough, too, one of the solutions of general relativity from Schwarzschild predicted the existence of what we now recognize as black holes. Of course, black holes have been predicted a long time ago, I think back in the 18th century, by a mathematician called Michel in England. And then later in France, there were suggestions. I think Laplace, in fact, had predicted that there should be things called black holes because gravity should somehow stop the light getting out. Now, the gravitational waves, they're the last unproven prediction, or they were the last unproven prediction of general relativity and hadn't been observed experimentally for 100 years. And in fact, for most of that 100 years, for the first 50 years or so, there was very little interest. It took 50 years before people began to work on it. And in fact, it was Joseph Weber at the University of Maryland who really woke the field up by claiming a discovery back in 1969, which was later shown to be false. What's happening now is, now we've detected the gravitational waves, so it is opening up a new astronomy, letting us see very violent events in the universe that may not give out light or any other electromagnetic signature. The trouble with general relativity is it's difficult to understand. I think even today, the number of people who really understand relativity is quite small. And certainly most experimentalists don't. There's no doubt about that. The equations are far too complex. But Einstein himself had quite a good model. I mean, he thought of the universe like being like a rubber sheet, and that we would like be little small two-dimensional beasts on that rubber sheet. And what, I'll put that back down again for a minute, what he predicted was that, well, that the gravitational waves would cause a strain in space-time, represented by the sheet here, and it would make something like this lattice move in and out, but just by a tiny amount. And of course, if we just go now onto the camera for a minute. No, didn't work. Try again. Right, so you can, I mean, what happens with the rubber sheet is that effectively mass curves that rubber sheet. And you can think of that as the sun curving space-time. And then if another object like the Earth comes along, it hopefully rotates round and round, orbits round and round, without crashing into the sun if there's no friction or no significant friction about. And what Einstein said was that what gravitational waves are kind of ripples on that surface, ripples in space-time, which are pulling and pushing as they pass by. Go back onto this. And this, in fact, is a very good explanation, I think, of what was happening. And it's one, certainly, that experimentalists very easily can understand, because they can understand the idea of a strain in space. You know, if you've got something that's of length L, it can increase in length by delta L. And in fact, there's something called the gravitational wave amplitude H, which is twice delta L over L. The trouble is that the delta L upon L that you can expect from most sources is something like 1 part in 10 to the 21 or 1 part in 10 to the 22. And of course, that begins to give some idea for why it's taken us so long to detect the signals. Now, what sort of things can cause gravitational wave signals? Well, rotating stars, particularly compact stars like neutron stars, or black holes rotating round and round each other and coming in and coalescing could be expected to radiate. And what you would expect to get from something like that is a chirrup of signal, something like that. And so what we've spent many, many years doing is listening for audio chirrups like that in a background of noise from our gravitational wave detectors. And it's not by chance that warships use that sort of thing as a siren against the noise of the sea, because it's, funnily enough, easier to pick out something that chirrups than something that has any other shape. Now, of course, also, you could expect that continuous waves, in fact, would be produced by pulsars, for example, because, I mean, something like a pulsar is asymmetrical very often, or expected to be, and as a pulsar rotates, you've got a change of shape, which should produce gravitational waves. But binary systems up here are certainly the ones that are most likely to produce things. Although there are people who believe that supernovae also will do that. So if you've got a star that is dying, it's running out of, of thermal energy, and so the gravitational effect becomes high. And what you saw there was the outer layer being blown off, while the center kind of went down to form a neutron star or a black hole or maybe a white dwarf. We'll see if we can run that one again. In fact, if I go back, so just watch the center of the star as it dies, and you'll see right in the middle there a little spot, which is probably a very compact object of some kind. Now, in fact, back in the days of Weber, at the beginning of looking for these things, everybody thought that supernovae would be the most likely type of event to produce gravitational waves. But in fact, the numerical relativity calculations now suggest they're a bit symmetric on the whole, and so they'll give out much less gravitational radiation than was originally expected. Also, of course, you could expect to have a kind of noise background, a sort of white noise background, a kind of hissing, coming about from what happened in the early universe, when the early universe was formed and was inflated up to higher frequency, effectively. And also, people believe that if cosmic strings exist, kind of strings of energy, almost like an extended black hole, that these might be like violin strings in the universe, and not only might they resonate like violin strings, but like a whip, they might actually crack, and we might be able to pick up these cracks, although we haven't got to that stage yet. Now, people, of course, were very unsure about the existence of gravitational waves until the binary pulsar system was found. This is a system of two neutron stars, one of which was a pulsar. And what one could do was to use the pulsar ticks, from the ticking of the pulsar as it rotates, to time the orbit decay of the binary. And if that is done, what you find is that general relativity, or the gravitational radiation predicted by general relativity, would carry off so much angular momentum and energy that, in fact, the orbit would evolve as the orbit kind of spirals in. And the theoretical curve is the continuous curve there. And the experimental measurements made by Hough and Taylor at Arecibo are the black points. And you'll see that the agreement is fantastic. So in fact, this was really the first thing that suggested that gravitational radiation was real and that it should be detectable. And for this, Hough and Taylor got the Nobel Prize. Now, how can we detect them? Well, it's exceedingly challenging because this gravitational wave amplitude is something like 10 to the minus 21, 10 to the minus 22, or even less. Now, that means if you go, say, objects a meter apart, let's suppose you have a bar that's a meter long, it will only move by 10 to the minus 22 of a meter. Now, given the size of an atom is 10 to the minus 10 meters, or a nucleus is about 10 to the minus 14 or 10 to the minus 15, what you're trying to do is look for something, a change that's maybe about a millionth or less of the diameter of an atomic nucleus. And that is not easy to do. Remember, the width of a human hair is about 50 microns. So it's really very, very big. Your hair is huge compared with any kind of movement that we're going to look for. So you need a very good ruler indeed to look for these things. Now, I'm not going to go into some of the early history, but people started off with aluminium bars in vacuum systems to stop sound getting in and isolated. We did that ourselves in Glasgow. That's how I started with Ron Drever in Glasgow. And we didn't, in fact, with these systems, see anything. And people realized that what you had to do was to make, because it's a strain in space, they had to make something that, that somehow allowed masses to be much further apart. And of course, you've got to worry about things like ground vibrations. So what they thought to use was a Michelson interferometer, which I'll explain in a minute. But to avoid things like ground noise being picked up, the mirrors on the system were to be suspended as pendulums. Now, there's something about a pendulum that is interesting, that if you move it very, very slowly, the bottom follows the top. If you move the top quite quickly, the bottom hardly moves at all. So something like that actually gives very good isolation against all sorts of nasty things that come in on the system from outside. Of course, you've got to watch. There's a resonant frequency also where the motion really builds up, and that has got to be handled by very careful sensing and electronic feedback to not to worry. So in fact, you can imagine now a Michelson interferometer like this, light comes in, it gets split two ways, up to one mirror here from a beam splitter, up to another mirror. The light comes back and interferes, and depending on the phase, you can have a bright fringe or a dark fringe or something in between. And you can imagine now that if the effect is a change of shape caused by the gravitational waves, where a circle changes into an ellipse, changes into a circle, changes into an ellipse like that, and you put one arm this way and one arm this way, there'll be a change of length as the gravitational wave passes. But it'll be a tiny, tiny change in length. And what you really need to do is to have the arm lengths big enough that the amount of movement that you get can actually be sensed. And that has been what we have been trying to do for, since with the interferometers, since about 1975 or so. What are we looking for? Well, remember, we're looking for coalescing objects. Neutron stars are black holes. And this shows a kind of merging black hole system. And you'll see that the black holes are rotating round about each other. And they're speeding up as they lose angular momentum and energy. It seems counterintuitive, that, but it's true. And as they come in together, bang, in the middle, you get something happening. And if it's black holes, you get a really new big black hole formed here in the center. Now, in fact, it turns out that that's exactly what we saw with our recent Michelson interferometers. Much to our great surprise, we had just turned the system on after upgrading the LIGO detectors, and I'll explain much more about that later. Suddenly we saw, if this is time and this is frequency up here, and the intensity is given by the color, suddenly we saw these very chirruping signals that, we were looking for. We were seeing these, or we were seeing one of these. Now, this was in September, about September the 15th, about 18 months ago, and we simply couldn't believe it. Everybody thought that it must be a false signal that somebody had put into the two interferometers we were using, the two LIGO interferometers, as some sort of test, because in previous experiments this had been done just to test us all out, where somebody would put secret signals in and see if we discovered them. And in one case, actually, we got as far as writing a paper on it, saying we had discovered something. And then we all went to a meeting, and we knew immediately, and it was to be champagne served because we might have found something, but there were plastic glasses, so we knew it wasn't going to be real. Immediately they saw the plastic glasses, we knew it wasn't real, and right enough it was announced, you know, haha, we put this in to see if you would find it. And of course we had. But this time everybody believed it might be the same, but because the system had just been turned on, everybody knew nothing had been put in. But it took from September to February for everybody to be sure, and so it took us that time to publish. And what we saw was, in fact, a very exciting black hole system where the black holes were, were coalescing. And in particular, I think what was particularly exciting was the size of the black holes. We published this in Physical Review Letters, because it turned out the black hole masses were 36 solar masses and 29 solar masses. And on the whole, people did not believe that you could get black holes of that size. They were quite happy with black holes of a few solar masses, which had been detected in other ways, let's say from how fast X-rays change, the kind of time the X-rays fluctuate from some X-ray systems. And they were very happy with huge black holes because they could see how these distorted the orbits of stars, like, the big black hole in our own galaxy. But to get something of this size seemed very doubtful. And in fact, just immediately after the discovery, I came back from Washington to give a talk in Warwick. And there was a woman in the audience who was exceedingly excited because she said she had a theory. I've been predicting these, and everybody was poo-pooing it. She was so excited it was unbelievable at the end of the talk because she felt she had been proved right, and indeed she was. Now, from the exact signal shape and time, we're able to get the masses of the individual black holes, these masses here. From the size of the signal, we can get the distance to the coalescence, and it turns out to be about 1.3 billion light years. Anyone know what was happening on the Earth at that time? Were there people? Anyone know? It was the first of the first cellular organisms were just being formed at this time on Earth when this thing set out towards us. Quite remarkable, really, that you see something from so far back. And I mean, the time scale is something like this. That was the signal, and you actually can see it by eye. And that was the other amazing thing. We had not expected ever to see something by eye. We were sure we need to do a lot of data analysis to see the signal. So great excitement everywhere over this. The mass, the mass of the black hole, the final black hole, was about 62 times the mass of the Sun, which is about 20 million times the mass of the Earth. The size is about the size of Iceland, 183 kilometers diameter, and it's going pretty fast, spinning at about 100 times a second. That means that in fact, the velocity at the equator is something like 0.4 times the speed of light. So in fact, this is a system which is highly relativistic, and what has been really remarkable is the progress in numerical relativity there has been over the last 10 to 15 years that actually could predict the shapes of something like this, and therefore allow us to interpret the signal, and decide about the masses. So actually, numerical relativity has been particularly useful for this detection. Now, in fact, about 3 solar masses were lost in gravitational radiation in about 0.2 of a second, and it turns out the luminosity at that point was something like 10 times the luminosity of the whole universe at that point. Of course, it doesn't go on forever, but instantaneously we were putting out more power than the rest of the universe in light, for example, which again was quite surprising. Now, there were 2 detectors running, 2 of these interferometers, not as simple as the ones I showed, but we'll come to that. And by looking at the time difference when the signal arrives at the 2 interferometers, you can set roughly where the signal has come from on the sky, but not with very much accuracy, and that is an issue. with 2 interferometers, you can't get good accuracy. You need at least 3 or more. And of course, as well as these LIGO detectors, as you'll see in a minute, there's also a detector in Italy called Virgo, which is also, it's not quite operating in its right form yet, but will come online over the next few months to help us get better accuracy. Now, it was amazing, the publicity. I believe there was about 900 newspaper articles, in fact, about it around the world. And of course, we were all highly buoyed up until Private Eye came along. And what Private Eye had to say was that a huge black hole opened yesterday in the public's understanding of what the latest scientific breakthrough was all about. This really brings you down to earth, you know. No light was shed at all by a huge, dense mass of newsprint which collapsed in on itself as it attempted to explain the importance of gravitational waves. The amount that the public understood about the subject was so microscopically small that at first instruments could not detect it. But after refinement, the comprehension level measured less than the billionth of an atom. Said one hurt astrophysicist, this could be the most significant lack of understanding since the last thing the public didn't understand. However, a member of the public was quick to congratulate the scientific community. Look, we're very happy that they are happy, and I'm sure the whole gravitational wave warp factor thing will help us defeat the Klingons and destroy the Death Star. Or is that the other way? Or is that the other one? Anyway, that was a good bit. So that was quite good. And also, I don't know if any of you have lived in the US, but there's a program called the Prairie Home Companion, and they ran a spoof on it also, which is particularly amusing as well. We detected a second event, and that was on Christmas Day in the US last year, Christmas 2015, or Boxing Day here, and that gave us enormous confidence that things were real when we got a second event. This was a different event. It's not very clear. You see, you can hardly see this one, actually. It really needed good data analysis to pick it out. It was a much longer event. It took longer than the first one. And in fact, the black holes involved were smaller. In this case, the black holes were about 14 and 7 solar masses, which was not so much of a surprise to everyone. In fact, but interesting, the distance is about the same, about 1.3 billion light years. So it's interesting that they're coming, these signals from about the same distance out in the universe. But this was a much less obvious signal, but nonetheless gave us great confidence. And really, there had been a lot of skepticism, even in the collaboration, about publishing the first one. But having seen a second one, that disappeared. And so we published this one, I think it was around about June, we published the second one. Now, I want you to listen to the kind of how the signal sounds. What these were the various whooping noises, and to tell you what you should have heard, with the first one you'd have heard a very sharp whoop. You can actually hear it, you know, and then and with the second one it's a very much slower whoop, and it's just to do with the size of the black holes. Now, going back now to the interferometers and saying a bit about interferometry. The first interferometers was actually set up by someone called Bob Forward in the Hughes Aircraft Lab in Malibu. He's a was a science fiction writer and owned a castle actually in Scotland. So he visited us, encouraged us greatly towards the idea of using interferometry. And other colleagues also, Ray Weiss in MIT, had the same sort of thought, and he built up an interferometer, as did our colleagues, in fact, in Garching, in the Max Planck Institute for Physics in Garching. They had bar detectors that we had in the early days and also moved into interferometers. And then in Glasgow, this is Ron Drever, who sadly died about just a few weeks ago. We set up a very simple interferometer, and just this shows a kind of the light path. Here we just had 2 bars and had an interferometer set up between the bars. These were second-hand bars we got from Rutherford Lab for free. And you'll see this was an argon laser, beautiful green argon laser light. And these were the days when you could smoke in the lab. You know, you were allowed to smoke. And that's how you're able to see the beams, because we were blowing smoke into it. These days are all gone. You can't do that anymore. Then we grew in Glasgow to a 10-meter setup. And then Drever had gone to Caltech, and he built a big American, of course. They had to build something bigger and better. And they built a 40-meter setup in Caltech, which eventually almost worked as well as the Glasgow one, but not quite. So our German colleagues and ourselves decided that we wanted to build something much bigger, because they were thinking in the US of building something much bigger based on the 40-meter thing. And in fact, we both, in both countries, tried to get money to build things that were kilometre scale. And in fact, I got a promise from SERC, it was at that point, of £5.5 million for the British end of this, and the German end had something similar. Then two things hit. SERC got a new chairman who discovered a huge black hole in the finance and who was not a sympathiser with gravitational waves and cancelled their money, and reunification took place in Germany. But luckily, the SERC changed into P-Park, and the chief executive of P-Park was much more sympathetic. And in Germany, the Max Planck Institute were becoming interested in things like this, and colleagues in Hanover decided that they could get money from the Volkswagen Foundation, also with Max Planck helping. And this led to us building a 600-meter detector near Hanover in Germany. Why is it 600 meters? Not much bigger, because I'll tell you the LIGO detectors, as we'll see, are 4 kilometers long. We simply couldn't raise enough money. But that turned out to be an advantage in life, actually. It was just as well that we weren't given funding to build something in Britain, because Britain would never have stuck with the project as long as other countries were willing to do. And it's just as well we had to build a small thing, because it meant we had to be much more technically aware and technically ahead of any other country. Well, that's us and our German colleagues. Now, in these interferometers, it's interesting to look at what the main limits to sensitivity are. Light, of course, is not continuous. It's not really a continuous wave. It consists of photons. So, in fact, you get what's called photon shot noise as the detectors pick up the light. It's just like taking a whole lot of peas and dropping them onto a surface. You hear the individual photons coming in. So in fact, it's the limits to sensitivity that you can measure very small changes. Similarly, there's radiation pressure. Light carries momentum, so if it shines off the wall and comes back, it actually pushes the wall a little bit. And you can imagine, if you've got mirrors hanging, the light pushes the mirrors. If you put these two things together, you find that, in fact, the sensitivity of the apparatus that you can build will be the same as given by the Heisenberg uncertainty principle. And this is known as the standard quantum limit. And for many years, people thought that this was the best you could ever do with interferometers. But it turns out that Heisenberg, the Heisenberg uncertainty principle says the uncertainty in position times the uncertainty in momentum has to be greater than a constant, which is Planck's constant. But it turns out to do that, Heisenberg assumed that position measurements and momentum measurements were not correlated. And it turns out that if you actually correlate position and momentum in some clever way, by how you build an interferometer, you can get around the Heisenberg limit. So it's not a true limit anymore to how well you can measure. It's, in a sense, what you do is entangle position with momentum. And effectively, instead of adding the two things in quadrature, delta x squared and delta p squared turned into x squared, instead of doing that, you add them linearly, taking the phase relationship into account. You find that one thing can kind of cancel the other thing and give you much better sensitivity. So that's a primary source of noise, photon shot noise and radiation pressure noise. Seismic noise clearly can be a problem, but you can filter that out using pendulums. Gravitational gradient noise is an interesting one. That is due to the actual Newtonian gravity effect of something moving close to your test masses. Like a fox is out running and he suddenly dies of a heart attack just close to one of your test masses, and it gives it a little jerk. And thermal noise, so is a real bugbear. The fact that you've got Brownian motion, thermal motion of the test masses and the kind of atoms and molecules in the suspensions. And that's the one that we in Glasgow have really been fighting for many, many years, and it is the primary limitation these days to gravitational wave detectors. But one thing these things all point to is that you want to have as big a signal as possible, you want to have as big a motion as possible, and so what you want is to have your masses as far apart as possible. Now, so you really want very long arm lengths. And what has happened is now that a global network of interferometers has been developed with long arm lengths. There's LIGO detectors in the US, one in the nuclear reservation at Hanford and one down in the swamps of Louisiana. It's got 4-kilometer arms, really long. There's the Virgo detector in Italy. This is the one that's not yet on the air in its final form, but will be quite soon, with 3-kilometer arms. There's our little GEO, 600-meter arms. And in Japan, they're working up to building in fact, they're already building a 3-kilometer detector under the Kamioka mine beside Kamiokande, the neutrino detector. And I'll say more also about possibilities in other countries shortly. Now, the initial LIGO detectors, as I say, they're big, and of course, due to the curvature of the Earth, you can't let the pipe follow the Earth. So in fact, the pipe has got to be dead straight to let the laser go along, and it looks very odd if you stand on the top here because the pipe appears to be rising as the horizon falls away. Down in Louisiana, things are very different because you've got swamp, in fact, due to digging out the kind of the ground material where you want to put the arms of the interferometer. And one of the exciting things in Louisiana is that when you have a swamp, you get alligators. And alligators are interesting beasts. I mean, they attract a lot of interest from people, but they're dangerous beasts. And what happened here was that one of the watchmen, the people who looked after the apparatus, every day went and fed the alligator with chicken. One day he didn't take the chicken, he just went and disturbed the water. Alligator wasn't pleased. Alligator came out of the water and chased him. So at that point, all the alligators had to be removed because everybody was frightened that a graduate student would be eaten, and NSF, who fund the graduate students, wouldn't have been too pleased by that if they'd actually lost someone down an alligator. Now, the interferometers are not nearly as simple as I showed. They've actually got Fabry-Perot cavities in the arms to increase kind of the signal size, because in a Fabry-Perot cavity, the light bounces up and down many, many times, a few hundred times. And you also do very clever things that impedance match in the laser light, so it all goes into the interferometer and nothing gets reflected back out. Usually, we're working just now at 1 micron with neodymium YAG lasers. Originally, we were working with about 12 watts of single line, single frequency, but now we have the ability to work up to about 200 watts, as I'll explain again later. Now, this is just a video showing the size of the system. Starts off showing how things are in Hanford, and then that's in Louisiana, and you'll see the swamp in Louisiana. These are like huge supermarkets. I mean, they're big things. The total cost of the system is probably of the order of $300 million or so. So, I mean, it's been very expensive, and it's why we were really very lucky not to have something in the UK or in Germany that was really big, because it would have been hard to have kept that level of funding going. Now, LIGO is a collaboration of many countries, and you'll see the number of countries here. I mean, it's interesting that Africa is totally missing and the Middle East is totally missing, but most of the rest of the world, in fact, are involved in LIGO. And the UK and Germany are actually the biggest grouping, apart from the US itself, inside the LIGO project. Now, we actually ran LIGO from 2001 to 2010 and saw no signals, and everybody knew we needed a 10 to the 15 sensitivity improvement. Now, in GEO, we had to be much cleverer, as I've said, and one of the things, as I also said, that bothers us is thermal noise. Now, thermal noise is motion of the atoms and the molecules in a system, and if you've got a resonance system, that gets concentrated into the resonances. Now, depending on the material that you use, you can have a broad resonance or a narrow resonance. And you take a plastic glass or something like that and try to ping it, and it's as dull as anything, very wide resonance. So the thermal noise is overall a whole range of frequencies. Take something metal like this and ding it, and it rings much more. So in fact, the width of the resonant peaks is much narrower, and the thermal noise tends to get concentrated in these peaks. If you ding a whiskey glass, it's even better. If you make a whiskey glass out of fused silica, it's even better still. Fused silica is a remarkable material. That's really synthetic quartz, in fact, non-crystalline, amorphous synthetic quartz. And so what we did was to make systems, in fact, which were all fused silica. And we made a double pendulum system here with more kind of stages, metal stages above, and we used silica fibers to hang one mass from another mass, and used a very interesting technique to make these things really almost monolithic silica. If there's any chemist present, we used sodium hydroxide and really sodium silicate to join bits of silica together, and then welded our fibers on. Everybody said we were crazy, that glass fibers were so weak that they would break. In fact, we've had this inside our geodetector for 14 years now without a single breakage. And in fact, they are very, very strong silica fibers. If you make them right, if you keep them under vacuum and don't let them get damp, they're even much stronger than steel, for example, than steel guitar strings. And they've got very narrow resonances, so it keeps the thermal noise down. So in fact, in the US, they had not been doing any of this research, and they didn't know how they were going to upgrade their detector, so they approached us to see if we could take the work we've been doing in geo and install it into the US detectors. And in fact, so we set out to install silica suspensions like this. Our German colleagues were making the best lasers in the world, and so they were asked to provide the lasers. And between us, we managed to get in the UK about £8 million, and Germany managed to get about the same in euros, and we went in strongly into the LIGO project to form what's known as advanced LIGO. Now the US did some things, of course, as you'll see as I talk about the engineering. They did the active seismic isolation to try to keep the thermal noise down. No, sorry, the ground noise down, and various other things. Now, in UK, it was RAL, Birmingham, Cardiff, Glasgow, and Strathclyde who did all this and formed our UK collaboration, as I say, working with our German colleagues. And if we look now at the kind of sensitivity that let's see if I can get the next. Well, this shows, in fact, how well we can measure. We can measure an H or a strain at best here of about 10 to the minus 23, which is certainly in the range where you might expect to see gravitational waves. In fact, you should be able to see out to about 70 megaparsecs for neutron star in spirals, and much further out for black holes. And just to give some idea of how things improved, we started with the LIGO detectors up about here, and then we, as I say, managed to, I'm using the wrong one, and then we managed to bring it down to this point here. Now, we're still not at full sensitivity. We've still got a factor of 3 to go in sensitivity in the LIGO detectors, but nonetheless, having made the detection, we're confident now that we can keep going and get this extra sensitivity. Now, to talk a wee bit about the engineering. The light must travel, of course, in an excellent vacuum, because you can only have a few atoms and molecules traversing the optical path, or you get excess noise. And so we'll work about 10 to the minus 8 to 10 to the minus 9 torr, millimeters of mercury. So it's a very good vacuum. In fact, it's the biggest and best vacuum system in the world. You've got to be careful, though. You've got to cover the tubes with things, because in the US you have hunters with bullets who shoot at you. And in fact, this happened in Louisiana. There are holes in the central station from where the hunters had been shooting at them. And I mean, the south of America is quite dangerous that way. And sometimes it's scary to visit because of that. The tubes are quite big, 1.2 meters diameter, but you do have accidents. Now, they tell me this was the police out looking for theorists because they prefer experimentalists to theorists, and trying to, I think it may have been terrorists they really meant, but we think it's theorists. Anyway, the poor policeman had forgotten the thing was there and managed to crash his car, which was totally written off into the system. He was okay. Now, it's big, 900 meter cube volume, and the surface area is big. It's all spiral welded. As I say, the vacuum's about 10 to the minus 9 torr at each observatory. The question is, if you've got a big vacuum system, how, in fact, do you go about finding a leak in the vacuum system? And we were indeed troubled by leaks, and it was very difficult to find, particularly in Louisiana. And it turned out that mouse pea is particularly corrosive if you've got stainless steel welds. And in Louisiana, they cover the tubes with insulation. And the mice love living in insulation and were relieving themselves in the welds. This ate through the welds and made holes and gave tiny vacuum leaks. In fact, I think they've got a cat now, so it's not a problem anymore. System's big. This just gives a general picture. You know, it's a system which is really designed for many instruments in the future. The laser is a neodymium YAG laser from Germany, 200 watts, stabilized. It's in both power and frequency. It uses a master oscillator, thing called, really related to something called an NPRO that many of you will have seen that came out of Stanford, in fact, followed by an injection-locked rod amplifier. And it's pretty good, not perfect, in fact. Nothing is, though. And then the mirrors themselves have got to be very, very special. They're 40 kilograms of silica, and they've got to be exceedingly flat and something like sub-angstrom smoothness. So in fact, they're quite difficult, in fact, to manufacture and cost a great deal of money. These test masses, of course, behave like 3 points in space. And the mechanical properties are really considerable, and it very much depends on the type of silica. For example, it turned out that by Corning silica, the masses actually change shape, whereas using heralds in Germany, the silica is very much better. And we've got great things to worry about in terms of figure, scatter, homogeneity, and also how good the coatings are, the optical coatings are. If you've got Fabry-Peros, some of you may remember from lab days, they're very narrow resonance and quite difficult to sometimes see fringes. And this is certainly true in LIGO. And our Australian consortium people found a system by putting in green light as well. They could somehow more easily, because the green light didn't resonate so much, manage to get the system started with rather nice fringes, then the switch over onto the infrared. And there's a telescope inside the vacuum which does that. Then we, of course, produced the silica suspensions. And if you look at the next one, this is a silica suspension being hit by a hammer. And it's quite remarkable, in fact, that you can hit it and make it bounce, and these fibers do not break. They're about 40 microns in diameter, and I think the stress in them is something like, I think it's something like 500 megapascals. And the breaking stress of the fibers is well into the gigapascals, stronger, as I say, than stainless steel. Seismic isolation is done in a number of stages. Some stages inside the vacuum. I think it's 2 inside the vacuum and one external one using feedback. I mean, it's a feedback system that senses the position and feeds back, you know, to kind of compensate for ground vibration. So there's a lot of really good engineering, mainly done by Stanford, in fact, for that. Now, very quickly, what about the future? Right, we've got to analyze the remainder of our data taken last year. We've got to improve the sensitivity of the interferometers, which we have a little bit. We started a second run in late November. We're hoping our Virgo detector will come along to let us get better sky resolution very soon. And we'll want to look for other signals from things like neutron stars, binary coalescences, etc. And in fact, having started this run, if you just watch the literature carefully over the next, in about 3 weeks' time, you should begin to see some new results coming out. But apparently, if I explain what they are, I'll be shot, so I can't do that. There's great secrecy. With 3 sites, this shows how well you can see things in the sky, and it's not very good, really. Still, if you want to, you know, contact your astronomy colleagues and ask them to point a telescope, it's kind of difficult. If you have 5 sites, you do very much better. So what we're aiming at is to go for 5 sites. And in fact, our Japanese colleagues, they're building this system in the Kamioka mine. It's actually cleverer than anybody else's just now because it's going to cool the masses at the end. It's going to use cryogenic cooled test masses at about 20 Kelvin to reduce the thermal noise. But that is going to be very challenging. We've been working with the Japanese on this, and there's some very interesting physics and engineering to be done on that. And then there's a spare LIGO detector I didn't really talk about, but there was a third one, which was initially then taken out, and that's going to go to India. The Indian government have decided to fund that, and in fact, NSF have agreed to it going to India. We have a site, in fact, in India, now approved, and people are beginning to visit to help them get it set up. And we hope to have Indian visitors next year also to try to help them understand, you know, what needs done in building these sort of systems. For the future, well, what do we need? We would like longer arms, and we'd like them underground to stop gravity gradient effects or to cut them down a bit. We'd like to put the power up. At the minute, each arm, the power is 800 kilowatts of laser light. That's a hell of a lot. We want to put it up to megawatts, to about 3 megawatts, which is really a lot of laser power, in fact. We want to use cryogenic optics. We want to use heavier masses so that radiation pressure effects, etc., are lower. We think we'll change wavelength. At least for some of the things, we'll go to 1550 nanometers and change to silicon, which is actually very similar to silica in performance, but works much better at low temperature. And then we're going to use something called squeezing, which is to remove the quantum fluctuations in the light. As I said earlier, you can do this with care, and already in GEO we have got squeezing working, and the US detectors will use this quite soon. Where are we going? Much bigger system in Europe, we hope, called the Einstein telescope, and it will have sensitivity that's something like maybe 10 times better or more than 10 times better than advanced LIGO. And in the US, there's a plan, this is a European thing, Einstein telescope. There's plans in the US to do similar things. Now in space, just one quick word, because I haven't got time to talk any more about it, but we have a plan for a space interferometer called LISA with 5 million kilometer arms. Why do that? Because you can look to much lower frequency if you have very long arms. And there's very interesting things happening as galaxies, you know, coalesce, etc. You have these massive black holes rotating round and round about each other when they coalesce. And so LISA will be mainly looking for huge black holes, whereas we've been looking for smaller black holes. So all in all, just to round off, we're going to have a network of facilities with advanced LIGO, advanced Virgo, CAGRA, our own GEO, LIGO India. We're going to have third generation detectors coming along relatively soon, and lab research is totally underway in that. We're doing a lot of research in Glasgow to the next generation. And in fact, we'll have this ET, we hope, in the mid-2020s or something like that, and similar things in the US. And then the space-based detector, LISA, will come along. And just to say, there was a demonstrator launched to test some of the ideas of LISA, drag-free satellites, etc., in 2015. And it's been exceedingly successful beyond all people's expectations. So ESA have decided that they will definitely fly this as a mission. We think it will fly about 2034. And I think all I can say is that we really are now in the days or in the time of gravitational wave astronomy, a new way to observe the universe. And being Kelvin professor, I do like, you know, to have the odd quotation from Kelvin. And Kelvin did say, when you are face to face with a difficulty, you're up against a discovery. And I've been face to face with a difficulty for well, it was about 45 years, and then the discovery came about. Thank you very much.